Hello everyone, my name is Sam Kai. My entry number is AE230076. Now I will design the PPI PID controller for the open load system by using the PID tuner Simulink. First, I will put the transfer function. And then the numerator we will change to the 10. And the denominator we will use the third order transfer function. We will set this one is to 10 and 5. This one is 0. And then apply, you'll get this one third order transfer function. Then we will put the step, the PID controller. And then the scope. And then the sum. And then we connect this component together. That's what this one is the open load system for the PID controller. And then we will set this PID controller to the P controller. And then we apply. And then OK. Then we double click again. You press the tune. Then the result will show that the P controller of the result is invalid. The graph is invalid. And then we press this the show parameter. And then this one parameter is for the P controller result. And then we change the P controller to the PI controller. And then we press the apply. And then we press the tune. And then we also get that the result is invalid. And we show the parameter. The parameter is the PI controller result. And then we change to the PID. And then the D we set to 1. And we apply again. And we press the tune. Then we will get that this one, the result also invalid. And we can show the parameter to see the PID of the detail of the result. And then this is the open load system for the PI PID controller.
Hi, my name is Yunje. Today I will going to design PPI PID controller for closed loop system by using PID tune simulate links. Now I'm going to start to construct the P controller closed loop system. The first we use step. The second we use sum. The third we use PID controller. The fourth we use transfer functions. The fifth we use scope. Then adjust the transfer functions to our transfer function use. If you make it bigger, it will appear the transfer function we use, and then complete the loop the system. And then this one sign. And we want to do the P controller. We double click this PID controller and then adjust into P. And we want to find the PID tunes. Press this tune. It will appear a PID. It will appear a PID tunes. So let us see the graph. This is a graph. Proportional. P stand for proportional. React proportional to the arrow and provide fast response and may lead to the state error and oscillations. Fast response, steady state. And if we want to see the parameter, we press this show parameter. Here appear P controller coastal system parameters at here. Now we do the PI. So same, double click this, it will appear this, and then change to PI and apply it, and we press 2. It will appear graph of this. It is combined with integrals. Integrals is used to emulate steady state error, but can introduce overshoots and slow response. And we press this show meter. It will show the PI controller closed loop here values. And now we will do the PID. Also same. Double click here, it will appear this, and we change to PID and then apply it. Tunes. It appear a graph like this. A better one because it's combined derivatives is used to the error change, improve stability and response speed. And we press this show meter. We will show the PID controller graph values that we want in here. This is the value. And that's all for me. Thank you.
Assalamualaikum, my name is Syed Muhammad Sulaiman Nasir PNG, method number AE230002. Okay, I will present about discussion for the result for open loop system. Okay, as you can see, for both PID tuner method block and PID tuner method tune has a same result and the same value of P controller, and PID controller. If it is 0 rise time and 0 settling time. Okay, from this result, we know that no one of the controller P or PID make the system stable for the open loop system. The reason is because the system parameter like rise time, settling time, and overshoot indicate no proper control as the output are undefined. Okay, as you can see, this is table of the result PID tuner. Result of closed loop system using PID tuner method block. Okay, from this result we can see P controller rise time 1.2 second, settling time 19.1, overshoot is 51.7%, and the stability for this controller is the system respond moderately quickly but takes too long to stabilize with a high overshoot, make it less stable. And then PI controller rise time 1.1 second, settling time 73 second, and overshoot 66.15%. Stability for this controller is has worse stable than the P controller due to the large overshoot and much slower settling time. The last one is PID controller. The rise time is 0.9 second, settling time 38.6 second, overshoot is 52.5%. Stability for this controller is the most stable because offering the best balance of fast rise time and reduced overshoot, but it still has room for improvement in terms of settling time and further reduction overshoot. Okay, the last one is the result of closed loop system using PID tuner method tune. Okay, for P controller we can see the rise time is 4.16 seconds, settling time 14.6 seconds, overshoot 8.48%, and the stability for this control is the P controller has a moderate response time and low overshoot, make it fairly stable with a good balance of speed and accuracy. And then for PI controller is rise time for is 7.71, settling time 70 seconds, overshoot is 70.5%. For this PI controller is longer to reach the target and has the higher overshoot, making it less stable than the P controller. Okay, and the last one is PID controller. Last time equal to 1.33 second, settling time 16.2, overshoot equal to 9.38%, and the stabilized for this controller is the fastest with a short settling time and a moderate overshoot, making it more stable controller overall. Okay.
Hello everyone, my name is Tong Kim Yao, and now I'm going to construct the P, PI, and PID controller for the Ziegler Nichols method. Firstly, we insert the transfer function blocks, and we double click to insert the data for the numerator and denominator. After that, we insert the step as the input, and we insert the sum as the feedback, and we change the sign After that, we insert the gain block to get the increasing gain for the sustain oscillation. Finally, we insert the scope block for the output. After that, we connect all the components together. So now we need to increase the gain value to obtain the sustain oscillation. So I will choose value 3. After that, we press the run and we double click on the scope to see the waveform. To get the sustain oscillation, we need to make sure that all the amplitude have the same amplitude. So now we have to try the another gain value to observe the sustain oscillation. So now the waveform show that all the amplitude across all the period are the same. And we can assume that the 4.9 is the gain value of KCR. To get the PCR, we need to press the cursor measurement. Then we need to adjust the cursor to the one period of the waveform. And then the PCR of the period oscillation will appear at here, which is equal to 2.8 something. So now this is the way to calculate the Kp, Ki, and Kd using the KCR and PCR that we obtained just now. This is the formula, and we will obtain the Kp is equal to 2.94, and we will obtain the Ki is equal to 2.085, and the Kd is equal to 1.036. After we get all the value of PID, we need to replace the gain blocks to the PID controller blocks. After that, let us simulate the P controller. Double click the PID controller, and then we choose the controller for P only, and then we insert the value that we just obtained. Now this is the step response for the P controller, and we click the show parameters, we'll show all the parameters of the P controller. Okay, next for the PI controller, we just need to modify the controller to PI and then insert the IE value, which is 2.085. And hence, this is the step response for the PI controller. And this is the parameter for the PI controller. Finally, for the PID controller, we need to modify the controller to PID and then insert the value for derivative, which is 1.036. Finally, the step response for PID controller in using Ziegler Nichols method will come out. And this is the final result. And press the show parameters will show the parameter for the PID controller. So I will pass the next present to the next presenter.
Assalamualaikum and good evening. My name is Ami Hakimi bin Maroni. Today I will explain about Ziegler Nichols method. First, the tables compare the performance of P, PI, and PID controllers using Ziegler Nichols method. In the first table, the block design results show that the P controllers achieve the fastest rise time of 0.64 seconds but has a highest overshoot of 81.1%. The PI controller has a long time rise with significant overshoot 136%. Meanwhile, the PID controller offers the shortest settling time of 30.8 seconds with a lower overshoot of 65.8%. In the second table, the twin system result demonstrate improvement in the performance. The P controller achieved minimum overshoot at 8.48% and shoot settling time of 40.6 seconds. The PI controller reduced overshoot to 17.5%, and the PID controller achieved the best balance with rise time 1.33 seconds, a settling time of 16.2 seconds, and low overshoot of 9.38%. Overall, Tani enhanced
the system performance with the PID controller providing the best trade-off between runtime, settling time, and overshoot. That's all from me. Thank you.